Yeah, today we're having some Joe telling us about some problems at Algebraic Torsion.
Okay, well, thanks so much for the invitation. It's always a pleasure to be at the Institute. So this is the second time ever that a talk has been given about my joint work with Aleksandra, Anna, Laura, Shira, and Luya about algebraic torsion of linear boundaries of concave plumbings. And every one of us has a different skill set. So, you know, if you're like really sad that I didn't get into the toric stuff, or that I didn't tell you all the fun topology or all the dynamics or the asymptotic expansion of curves, or hopefully I tell you how to put some of these ingredients together, then you can reach out to one of my collaborators and let them know. And we've been working on this project, I guess, for about a year and a half. We were fortunate to come to the IES Summer Collaborators Program this past July. We made a lot of great progress. Highly recommend the IES Summer Collaborators Program for others. We're still all talking to each other at the end, even though we found a couple of gaps in our arguments, which we have since filled in, but it's not like over Wolfach where I'm told that if you like spend 2 weeks with your collaborator there, you want to like have one less person in your collaboration. Or you make up a friend in Freiburg. This is like the options. Anyways. Okay, so I wanted to start a little bit with some motivation for what it is that we're doing. And then I'll tell you a little bit about like what a linear plumbing is, what algebraic torsion is, and all that fun stuff. So eventually, the goal of our group kind of mathematics is to find examples of contact manifolds which are tight but not fillable. So I put an over-twisted disk on this slide, and the manifold is called over-twisted if you can find one of these disks in it. Otherwise, it's called tight. So this is the dichotomy that goes back to Eliashberg in the 89, 92 time. And then shortly after Yasha approved or established this tight versus over-twisted dichotomy, he realized that you could use Gromov's homomorphic curves to show that symplectically fillable contact structures are actually tight, but there are not really so many examples known of tight contact structures which are not fillable. There's like a couple due to Etnayer and Honda, but really people don't understand what prevents something from being tight but not fillable. And we have some kind of like a class of examples in mind that are coming from more general plumbings. But as a toy case, we thought we would first consider linear plumbings. It already turned into like a very serious undertaking, but the expectation is that all the tools we developed for linear plumbings will kind of carry us through and allow us to study some examples we have in mind that comes from work of Laura Starkston and Marco Gola. And then so that's kind of like a long-term goal, or it's more long-term than we expected. And then in the kind of the like immediate term, what we did do was develop a lot of methods for embedded contact homology to study topologically interesting manifolds. So embedded contact homology is one of the three-dimensional gauge theories. The other two are monopole Seiberg-Witten Floer homology. And then there's, of course, Hagard Floer homology. And those have had kind of like spectacular results in the world of low-dimensional topology. But embedded contact homology has been kind of more focused on dynamics. And there's a really nice Weil law, so people haven't been kind of as active in trying to understand how to use ECH to do something fun with topologically interesting manifolds. ECH has pretty much been relegated to tight lens spaces of a very particular flavor coming from quotients of rational ellipsoids. There's the S3, there's S1 cross S2, and T3. So there's not like a lot of topologically interesting manifolds that we know how to compute ECH of. So we developed a lot of tools to start to do that. And then the third kind of goal of the project was to try to understand something about algebraic torsion, which is itself like not very well understood, and there's not really a lot of literature on the subject. So it first arose in 2011. Lachev and Wendell wrote a paper, and they were inspired by the BV infinity structure in SFT to try to come up with some additional information associated to topologically interesting curves. And then Michael was at the MSRI at the same time as them and figured out like over a weekend that a lot of the structure they found in the SFT world had an analogy in the ECH world. So he wrote a short appendix, and then nobody really did that much with Michael's appendix except that Chatai, Gordana, Jeremy, and Andy Wand attempted for well, about a decade to try to understand how to import algebraic torsion in the ECH setting to the Heggard-Floer setting. And I think the four of them have various opinions about that project, but you know, people have kind of, it has like really spectacular applications if you can do something with it, but it is very hard to understand because at the end of the day, you're looking at some topological information associated to J-holomorphic curves and trying to get a refined understanding of the topological complexity of those curves. And, you know, that itself is like a pretty serious undertaking. And then in the SFT setting, there has been a lot of work by Agustin Marino, and then also in joint work with Zhengi on trying to understand some of the structure that algebraic torsion gives you in SFT. So there has been kind of some work, but there aren't really like a lot of examples computed in the wild. And so far, the only kind of like topologically interesting algebraic torsion, J-holomorphic curves that have been found have been basically macaroni noodles where you just have a cylinder with two positive ends or a plane. And so the hope is that when we get to these more topologically interesting manifolds, we'll be able to get some more kind of interesting holomorphic curves, which will give us higher algebraic torsion values. And then I have my like joke that turns out to be not so much of a joke about how you'll spend a decade doing any activity in contact homology. So anyways, okay. So with that being said, I want to kind of like set the stage for what it is that the class of manifolds that we're going to be studying. So we looked at linear plumbings of disk bundles. You can look at tree-like plumbings of disk bundles, but we thought, you know, let's just try it with linear plumbings and see what happens. And we already kind of bit off a lot. So with a plumbing, this is a construction that goes back to Milner, and he used it to construct exotic manifolds, exotic spheres and whatnot. So it's a really nice kind of like gluing construction, and it is relatively intuitive at the end of the day. And then it turns out in the symplectic realm, there are really nice models for it given by Gay and Stipschitz. So the data that we have associated to a plumbing is going to be some finite connected graph. It's usually a tree. In our case, it's going to be linear. And then associated to each part of the graph, you have vertices. Those vertices get labeled with some genus, and that's the genus of the base of the disk bundle. And then SI corresponds to the self-intersection or Euler number of that disk bundle. And then they have some valency that corresponds to how many other vertices are attached by connected to each other. And then there's also signed edges between the vertices if you want to do fun things with orientations, but we're not going to do fun things with orientation. So the sign associated to all the edges is going to be a +1. And the basic construction is that you're going to be swapping the fibers of one bundle with the disks in the base. We're going to be gluing, in the linear case, a di cross d2 to a di +1 cross a d2. We're going to swap the factors but preserve the product structure. And then there's a way to write down a plumbing graph in terms of a matrix. And basically along the diagonal, you just write down the Euler numbers. And then the other numbers are ones, which correspond to each disk bundle being glued to exactly one other disk bundle. And that's kind of the information that you read off from this plumbing graph. And then there's a symplectic structure that you can naturally associate to any plumbing. So for each disk bundle, what you're going to do is set up the zero section to be a symplectic surface. And then the disk bundle itself will be some standard small symplectic neighborhood of that zero section. And then the plumbing gluing is going to be a symplectomorphism if you arrange for the symplectic area of the fibers to be the same as the symplectic area of the bases, where you've got, symplectic form attached to each disk bundle. And then when you do this symplectically, you'll have a vector of areas corresponding to each zero section. And you do have kind of like some choices here, but they're disk bundles, so you're not doing anything like terribly fancy. Then we have some kind of more verbiage to discuss. So this plumbing construction, if we associate this extra symplectic information, it's going to be a closed symplectic manifold, which I've written as W omega with boundary, and the boundary is this Y lambda, and we have that it's going to be a strong, there's a strong, I don't want to say it's a strong filling, because there's a kind of an orientation condition that happens that tells you if you have either a convex or a concave boundary. If you have a convex boundary, then this plumbing would correspond to a strong symplectic filling. But when you're concave, you're not actually a filling, it's like going in the opposite direction. And so this convexity or concavity just has to do with the fact if the primitive on the boundary gives you a contact form, so that the volume form associated to that contact form gives you an orientation, which agrees with the orientation of the contact manifold as the boundary of the symplectic 4 manifold. If that orientation disagrees, then you say it's concave. And this convex concave is equivalent to the existence of a Liouville vector field that's either outward pointing in the convex case or it's inward pointing in the concave case. And then these concave fillings of symplectic manifolds, or these concave fillings of contact manifolds are kind of like a really exciting topological playground. And Gay Stipschitz gave a really nice description of when from this plumbing graph intersection form, and they did this for more general tree-like plumbings. What are the conditions you need so that you're guaranteed a convex boundary, so a contact boundary of convex type, and the condition that you need is for the plumbing form to be negative definite, which is a thing you can check if you have kind of an explicit example, or in some cases, if you're doing some kind of linear plumbing, you can check it by hand. And then we were interested in concave contact structures induced by the boundary of the plumbing. And so Lee Mack did a slight generalization and reworking of the Gay-Stipschitz formalism, and they showed that you get a concave structure if there's some negative, if there's some vector z that's negative in every entry, so that minus q times z gives you the vector of symplectic areas. So there's a linear algebra or two linear algebra conditions at the end of the day that you can check, and everything is like relatively hands-on. It's just that there's like kind of quite a bit to unpack. And then the linear plumbings we consider are lens spaces. So I think this kind of goes back to work of Neumann, but then we kind of also were able to redo this in a symplectic setting using toric constructions. And then you may wonder, like, why do we already kind of know what lens spaces are fillable or not, and then we know the fillable ones are tight, and the non-fillable ones are over-twisted, and that goes back to work of Liska. And the way he did that was to consider embeddings into closed symplectic manifolds, because if you have a convex filling and a concave filling, you can glue them together. You end up with a closed symplectic manifold. There are some kind of homological restrictions that you have when you do some blow-up procedure. And then McDuff-Gromov tells you that non-embeddability is something that you can kind of check hands-on with a homology computation. Especially if when you glue your convex and concave fillings together and you get a rational homology sphere, that's something that you can do. And then it turns out that non-embeddability actually obstructs realizability of singular curves in algebraic geometry via a blow-up procedure. And the point is that in the algebraic geometry world, degree genus constraints are not enough. And there are like whole programs to try to understand realizability of certain singular curves. And so it would be really nice if we could use some methods from the contact realm to actually give us some obstructions to realizability, which was kind of like the motivation for the project in some broader sense. And then another thing that I wanted to say is that Honda and Giroux classified fillability of lens spaces as well, but kind of like Liska was maybe the first one that kind of really started this program of classifying fillings. And then also most of the characterizations of kind of like tight fillable things, a lot of that goes back to the use of the contact invariant in Haggard-Floer homology. And that was something that Liska did a lot of work on, as well as Paulo Cigini. And so there's kind of like a lot of like fun topology and some analysis and geometric things going on in the background that motivated this project. And we hoped, you know, we would finish, and well, we have finished in finite time our project for linear plumbings, but we do kind of like want to go into more exciting plumbings that are tree-like. But for today, we're just going to focus on linear plumbings. And what I kind of want to do next is tell you like a tale of two approaches to prove the same theorem. Really, there's like 3 or 4 approaches if we also consider the work of Liska and Honda Giroux. But, you know, at least we know that we're all converging to the same content. And also there's no kind of like sign error that we have to worry about like there was with respect to another like three team situation. Okay, so I guess I should like briefly pause. Is everyone okay with the backstory? Okay, great. I wanted to make sure, well, if Luya was lost, then like all hope would be lost. But so one nice thing that we have to our favor is that there are explicit local toric models. So these were worked out in kind of gory detail by Gay and Stipschitz. And without kind of like going into too many details, you can write everything down in terms of a product symplectic structure. You can write down the Liouville vector field explicitly. You can write down the contact form. And then the kind of linear algebra condition I told you about previously, you can check by hand to see that it ensures if the Liouville vector field is inward pointing or outward pointing. And it turns out that that linear algebra condition to produce that the resulting boundary is a concave contact boundary of the plumbing is going to force these ZIs that show up to be negative in your local toric model. And then there's kind of 2 sets of coordinates, one coming from the torus coordinates and another set of coordinates on the base. And then the idea is that like in collar neighborhoods, you're swapping the disks fibers with the base. And so you can kind of like write down each of these pieces and then figure out how they all glue together, and everything is given kind of locally. But then as we started to work through this, we wanted to try to have kind of a variety of contact forms at our disposal to do these computations for embedded contact homology. And so we realized that if we like really thought very deeply about linear algebra and coordinate transformations, we could come up with an explicit global toric structure for linear plumbings. So I put kind of like 2 examples, which we won't really go through, but they're there to kind of like show you that I'm not telling lies. So the idea here is that in this figure, we've got kind of like the 2 pieces that we're going to end up gluing together. We have like local models that we know are given to us by the input data. Here we're gluing a 0 SN to a 0 SN minus 1. And then there's a way to do the coordinate transformation, which we wrote out here, so that you can actually glue this blue guy to that blue guy. And now you have a global toric model for the plumbing going from 0 SN to 0 SN minus 1. And then you can kind of like iterate this procedure. And so, but you do kind of have to like fix some data like the symplectic areas. But the symplectic areas are not really so important for the project at hand because we're trying to compute something purely about the contact information. And so here's a global toric moment map image for the plumbing -2, 1, 0, -2. And then we kind of assign some symplectic areas 1, 7, 4, 1, so that all of the vectors have are correctly drawn and whatnot. But the nice thing now about this global toric model is that over each of the vertices, we basically just have a pre-quantization bundle type contact form. And then along the green line, that's kind of basically a moment map curve. And then at each point where there's a rational slope, we're gonna have a torus of Rabe orbits. And then we'll be able to work with that to do some perturbations to try to compute some portion of the embedded contact homology chain complex. Having this global model is also useful from a toric perspective, and it also let us understand how to say which plumbings were actually like which lens spaces. Great, and then I guess I kind of already mentioned this, but the induced contact form has product symmetry, and then the Rabe dynamics are explicit. We have a more spot contact form, and then we can kind of play with what moment map images we want to use when we actually like sit down and do our computations. So the next thing I wanted to talk about is some results that we obtained using toric methods. So work by Eugene Lehrman going back to the early 2000s gives a description of contact manifolds in a toric setting. They all have to be lens spaces. And then it turns out that the contact manifold up to contactomorphism is determined by two rays and the angle between them. And that's giving you basically the moment cone, and then you have kind of some choice of a curve, which is giving you the specific contact form that you're picking. But at the end of the day, the curve that you pick is independent of like the contact structure. All the information you need is encoded by the rays and the angle between them. And it turns out that if the angle is less than or equal to pi, you get the tight canonical contact structure on a lens space. If the angle is bigger than pi, you have an overtwisted contact structure on a lens space. And here, like the moment cone, is just whatever the angle is. When you get to have an angle that's bigger than 2 pi, then the moment cone is all of R2. But the point is that when you add 2 pi to any angle, that corresponds to a Lutz twist. And so the homotopy class of plane fields is going to be preserved. And so you have the same overtwisted contact structure. So then really all we care about is the two rays and the angle between them. And just as like it's probably not a sanity check for anyone in this room because no one I think in this room does toric contact or symplectic geometry. But if the two rays that you were given were -1, 0 and -L minus K, and they're pointing towards the origin, then the boundary is going to be diffeomorphic to the lens space LKL. You can like do that explicitly. It's basically redoing a computation by Neumann with some like a little bit more input from Lehrman. And then because we were able to stitch everything together to get a global toric description for our linear plumbings, that meant that we could just kind of like read off what the moment cone ended up being so that we could characterize if a linear plumbing was tight or over twisted. So this is our these are like the kind of two results we proved using toric methods and doing some really deep thinking coordinate transformations. And we were, you know, it's always kind of reassuring if you can prove something without holomorphic curves. And then it also kind of like gave us a idea of what result to expect if we did prove it with holomorphic curves. And a neat thing that happened is that we really saw this like angle between the two rays in the construction of our the holomorphic curves that we came up with, if we could prove that a plane was unique or not. And that in turn gave us information about the non-vanishing or vanishing of the contact invariant. And then also we were able to do something with algebraic torsion as well. And I don't know, it depends on kind of like what side of the symplectic community you're on. If you are really excited about toric stuff, then you're probably like excited to hear that like you could bypass pseudo-holomorphic curve methods with toric geometry. If you're like very entrenched on the holomorphic curve side, you may be very delighted that you could recover the same results using holomorphic curves. And if you're not sure like which side you're on, you're probably like reassured that you could come at it both ways. And our group was like very happy that we had this nice like toric, purely toric theorem, because like whenever we would start to have some headaches with holomorphic curves, we'd always say like, well, at least we still have a theorem. There are some like borderline cases that we can't quite do, but you probably can't even really tell from the numerology on this slide. But you can do them kind of like hand by hand, but the linear algebra just doesn't work out nicely in terms of the linear transformations and trying to determine the angle between the defining rays. But it is like a very like kind of complete set. And then most of kind of the results going back to Neumann didn't allow one of the relative Euler numbers assigned to a vertex to be 0. And so we could like recover that information.
So when you prove it's tight, so you say you don't use pseudoromorphic,
yeah,
nothing. So how do you prove that there's no over-twisted disk?
Because we can write down the rays and the contact in the toric world and figure out that the angle is less than or equal to pi.
So assuming there's an over-twisted disk, you can conclude that that could not be true, or what do you do?
Oh, okay, I see. So you're asking like, where is the over-twisted disk?
I mean, you say it's tight, so you show there's no over-twisted disk.
Yeah, so Lerman, that like goes back to Lerman.
Okay, so there was some technology there.
Yeah. So this, yeah, we're relying on Lerman's classification of toric contact manifolds and his ability to obstruct an over-twisted disk. And then you can actually construct the over-twisted disk when the angle is greater than pi. But we could just use what he did pretty much like off the shelf once we figured out how to write down the rays that correspond to the boundary of the linear planes. And I am not the toric expert, and that result I think we proved almost a year ago, and so yes. And I would say, yeah, it's really like remarkable what the toric people can do. And Aleksandra is our like toric expert. And she had been saying that this paper by Lerman is like pretty underappreciated, but it's one of her favorites. I remember correctly. Okay, so then for the last like however long people can stand, I was going to tell you about our results in the pseudo-holomorphic curve world and what all is involved there. So here I've tagged our theorem as an almost theorem. So I guess before this morning, we thought there was like one case that we had to check, but then Luya and I convinced ourselves that we remembered the correct technology and can like combine all like, I don't know, there's probably like 20 lemmas together to actually like get this theorem, but we have to consult with our co-authors before we remove the almost. And so here we state it in terms of the corresponding moment cone. And then the idea is that you could go back to the previous set of results to actually like read off what the moment cone is going to be. but we do at least kind of like can be reassured that the toric world is like knowing something about what's going on in the holomorphic curve world. And then the way that we prove that the contact invariant vanishes or not, or that we can get a bound on algebraic torsion or not, really like is coming from the moment cone picture, which is nice. And so a few kind of things to maybe like that I want to like touch on a little bit is that algebraic torsion is not actually an invariant. Well, we don't know whether or not it's an invariant in the ECH setting. So in the ECH setting, or I guess algebraic torsion in general, was kind of billed as a refinement of the contact invariant in the sense that it could see the topological complexity of the curves that could kill the empty set. And in ECH, the contact invariant is just the class of the empty set. And so that's why there's this kind of like idea of a refinement to see like topological complexity of what kills the empty set, and a plane has the lowest topological complexity that kills the empty set. But the contact invariant doesn't really like know the difference between whether it's a plane or a macaroni noodle or something more exciting. But we don't actually like know whether or not algebraic torsion is an invariant in the ECH setting. In the SFT setting, you need the BV infinity algebra of SFT to say that it's an invariant of the contact structure. And then in the Heegard-Floer world, well, you would have to talk to Andy, Gordana, Jeremy, and Chatai to sort out like just how.
They took like a super.
Yeah, they did like a lim soup thing, so they got an invariant, but then computing it in practice turned out to be like not as feasible as they like hoped. We make no bold claims about whether or not it's an invariant, and we do compute it for kind of any choice of non-degenerate contact form and generic J associated to the contact toric manifold. But we were in kind of like a special situation where we could look at cobordisms. There's it's not an easier version of algebraic torsion. So there's this AT subscript simp. So simp stands for simple, but I would not say that like simple algebraic torsion is like a more easy or intuitive version of algebraic torsion. But it's called AT simp because you don't have to worry about terrible things happening in cobordisms with your holomorphic curves. And so you have a well-defined enough chain map in order to establish a weak neutrality property. And then along the way, in kind of like establishing the vanishing or whether or not the algebraic torsion vanishes or if it's infinity, we had
what
like.
does it mean? So if algebraic torsion vanishes and you have a plane?
Yeah, basically that you have a plane that kills the empty set. So there's going to be a spectral
And
sequence.
if it's infinite, you don't have anything.
Then nothing, the like empty set survives like indefinitely on every page. And I think, well, I'll have this in a moment, but basically what is known is that if you are over twisted, then the algebraic torsion is 0, but it's not known if algebraic torsion 0 implies that the contact invariant vanishes. So you have to do those things kind of like separately. And then similarly, like it's not known if algebraic torsion being infinity implies that the contact invariant is non-vanishing, even though that is like what you would expect. And then to actually like go kind of in the opposite direction, you want to actually like sit down and like write out your holomorphic curves. I guess like you don't like, yeah. More questions, comments, thoughts? Ready for the definition of algebraic torsion in ECH? John is nodding his head, but he might not be in a slide or two. Okay, so Yeah, so along the way to proving our almost theorem, we developed a much better understanding of holomorphic curves and planes. I would say like we feel like we very much understand holomorphic planes in this contact toric setting, and establishing their uniqueness. We can construct them. We can figure out like what side of a Morse spot torus they live on. We use like pretty much every ingredient in the holomorphic curve toolkit. So we use a junction, we use Seifrin's asymptotic expansion, we use intersection positivity, we use action constraints. So we just like throw everything at everything. And then what I kind of like want to do is elucidate some of the ideas and difficulties that we had kind of like along the way and why it's so difficult to understand algebraic torsion. And then also I wanted to give a shout out to Helmut's pseudo-holomorphic planes in the early 90s for the Weinstein conjecture. So that I guess kind of like really kick-started SFT, and then also this kind of like idea of understanding if there's more than just a plane or if it has more topological complexity was the starting point for Yanko and Chris's algebraic torsion project. So we have Helmut to thank for all of this complexity. Okay, so because I'm gonna like tell you guys some things about ECH, I think everybody in this room knows these words, but they're here in case you don't, and then they also kind of just set notation. So given some embedded Rabe orbit, the linearized flow along the orbit restricted to the contact distribution gives you a symplectic linear map. If one is not an eigenvalue of the linearized return map, you say the Rabe orbit is non-degenerate. The contact form is non-degenerate if all the Rabe orbits associated to it are non-degenerate. And then in dimension 3, we know what a 2x2 symplectic matrix looks like. And so we can classify non-degenerate orbits as being either elliptic or hyperbolic according to whether or not you have eigenvalues on S1, in which case you're said to be elliptic, or if you have real eigenvalues, then you're said to be hyperbolic. If your eigenvalues are negative, you're negative hyperbolic. If your eigenvalues are positive, you're positive hyperbolic. And then we know how the Conley-Zander index behaves for the elliptic and the hyperbolic Rabe orbits, and everything can be very explicit. And then in like one slide, not later, well, that is later, we're gonna talk about pseudo-holomorphic curves. So we're gonna use an almost complex structure, which is R invariant. We want it to be an endomorphism of the contact distribution, and we want it to rotate the contact distribution positively with respect to the symplectic form given by d lambda. And then you want it to interchange the R coordinate of the symplectization with the Rabe direction. Great. And then this is my attempt to do embedded contact homology on a single slide. Well, I guess there's two slides. So embedded contact homology is a gauge theory for contact 3 manifolds. You also need an input of an H1 class, and it's due to Hutchings. And so he's deeply inspired by Taubes's work on the Gromov invariant. And basically the idea was to try to come up with the kind of like Gromov invariant counterpoint to monopoles, Seiberg-Witten Floer homology. And in that kind of like end, the chain complex is generated by Rabe currents. And so I called them currents because we just care about the data of an embedded Rabe orbit and some multiplicity. We don't care if like the generator is like going around an embedded orbit 3 times or 2 times, or we go around the embedded orbit once and we have 4 copies of it. We just keep track of some integer. And then we also have this extra stipulation that we don't allow kind of like arbitrary Rabe currents. If the embedded orbit is hyperbolic, then you're only allowed to attach a multiplicity 1 to it. And there are reasons for that, but they're not kind of like easy to explain in 5 minutes. But there is kind of like a counterpoint using a mapping torus construction as to like why you would expect that. And then also in the SFT world, you have to like throw out certain iterates of hyperbolic orbits. So they just kind of like mess life up a little bit. And then you need the sum of the homology classes to be equal to gamma, where gamma is some fixed H1 class. And what's kind of unique about this embedded contact homology story as compared with the kind of like all the various Floer theories in the symplectic and contact realm is that the grading isn't given by a Fredholm index, it's given by something called the ECH index, which is a topological index. And it has some of the same kind of like ingredients as the Fredholm index, but it's not the same, and it has a new ingredient, which is the relative self-intersection pairing. So you've got a relative Chern number, you've got a Conley-Zander term, and you've got this relative self-intersection pairing. And it turns out that the ECH index is actually topological. So if your curve was actually to be just some relative second homology class, it turns out that that's the only thing that the ECH index would depend on, and not actually on a choice of curve, which is like kind of a surprising feature. And the reason why ECH works is because you have an index inequality. So you have that the Fredholm index of a curve is bounded above by the ECH index minus twice the count of singularities. And so because of that, that's true if you're somewhere injective. And so because of that, you get that if you are ECH index 1, your Fredholm index is 1 and you're embedded. And so that's why it's called embedded contact homology. And the ECH index gives you a relative Z mod D grading, where D is the divisibility of the first Chern class of the bundle plus twice the Poincare dual of the first homology class in H upper 2 mod torsion. So anyways, you can do like a lot of things with the ECH index, and we'll get to play with its counterpart to define algebraic torsion. And then the ECH differential counts currents, which is similar to what Taubes did in his work in showing that the Gromov invariant equals the Seiberg-Witten invariant. And it also turns out that low index currents are realized by unions of holomorphic curves. And so you can kind of get away with thinking of the ECH differential as counting holomorphic curves, union trivial cylinders assigned with some multiplicity, but secretly the reason kind of why the theory works is because you're using currents. And so you have access to Taubes's nice compactness results for currents. And then I tried to summarize some of the work that went into doing ECH with haikus. So the first one is the index inequality paper. So there's partition, Reithfun, index inequality, Hiei for adjunction. And it's how you end up defining the ECH index and getting that it gives an upper bound on the Fredholm index. There were a lot of like fun things that show up in that paper. And then the other haiku I think was a little bit more laborious to write, since that was like 200 pages, whereas the first haiku was 30 pages. So that haiku says that D squared is 0 and obstruction bundle gluing is complicated. So we're not going to get into these stories, but the kind of point to say is that there's a lot of stuff that's lurking behind ECH, and a lot of kind of like one also intermediate step in going from the 2002 haiku to the 2007, 2009 haiku were some of Seifring's asymptotic results, so that you actually had an asymptotic expansion of the ends of your pseudo-holomorphic curves. And then Seifring's work was, of course, motivated by a lot of SFT, and so the development of ECH kind of paralleled in some respects the development of SFT, and there are similarities between the two theories, but ECH is kind of more, belongs more in the realm of gauge theories as opposed to SFT. So then you may wonder, okay, great, what are we going to do with ECH if we just know that it's a homology theory? And so luckily, Taubes is really good at analysis. Oh yeah, sorry, this is like from when it's a Beamer talk and I click through everything again. I guess it's like good here too. So Taubes has this great 500-page theorem that says that if your three manifold is connected, then there's a canonical isomorphism of relatively graded Z mod U modules, where U is a U map, which decreases the grading by 2. And you have this isomorphism between embedded contact homology and appropriate flavor of monopole Seiberg-Witten-Floer homology. Seiberg-Witten-Floer homology requires the input of a spin C structure. The picture on the right is supposed to kind of represent a spinner. I learned that there's a fun story involving a professor at the University of Chicago where he was trying to illustrate an element of a spin group using his cell phone and his arm, and he just slammed the cell phone on the table and smashed the screen. Didn't quite get to the 720-degree rotation that would have returned the cell phone back to the same spot. So if you do that trick with your arm, maybe don't use your cell phone. Anyways, that's neither here nor there. And the other great thing about Taubes' theorem is he showed that it, anyways, so the point is that Kronheimer and Marofka rigorously showed that monopole Seiberg-Witten-Floer homology has all the properties that you need it to have. And so because of this canonical isomorphism, you know that ECH doesn't actually depend on the choice of contact form or the choice of almost complex structure. And it's actually stronger than just an invariant of the contact structure. It's actually a topological invariant. And then the way that you would kind of see the topological invariantiness is to know that you have to shift this choice of first homology class when you change the choice of the contact distribution so that you get the right spin C structure plus the Poincare dual of gamma. And the other thing that Taubes showed is that he showed that this isomorphism also sends the ECH contact invariant to the Seiberg-Witten-Floer contact invariant. And so it's maybe kind of strong to say that it's the ECH contact invariant. It's just like an ECH thing that gets sent to the Seiberg-Witten-Floer contact invariant. So you know that it's actually a contact invariant in ECH. And then the slogan that you hear is that in ECH, you get a free contact invariant coming from the class of the empty set. So I just wanted to underscore that maybe free should be in quotes because it's coming via Taubes' work and Kronheimer and Marofka's work.
So the conclusion that ECH is a topological invariant, is that through Taubes' theorem?
Yeah, that's through
Is that the only proof of this fact today?
That's the only proof of this fact today. There was some hope that maybe you could do that you could remove the dependence of J purely using holomorphic curves, but people gave up on trying to do that. And the kind of main issue that shows up is that when you work in cobordisms, you have no control over the Fredholm index of the curves in the cobordisms, and you can have multiply covered components, and life just breaks down.
So it's transversality.
Yeah, transversality and compactness issues, which are just completely circumvented via this isomorphism. And then I guess with I have 10 minutes left, so I have some fun facts about the contact invariant. So the Seiberg-Witten-Floer contact invariant was implicitly defined by Kronheimer and Marofka in 97, and then work by Mariano Echeverria established the naturality property for the Seiberg-Witten-Floer contact invariant, meaning that it's preserved under strong symplectic cobordisms. So that itself involved a lot of work and an upgrade of a gluing theorem of Marofka and Roland. And then if your contact manifold is overtwisted, then the contact invariant vanishes because you have the existence of an embedded hyperbolic Rabe orbit, which has the smallest action, and you know that it bounds a unique Fredholm and ECH index 1 plane. And a big part of the story and what we were trying to do ended up to try to prove the existence of this unique Fredholm and ECH index 1 plane without knowing that whether or not our linear plumbing gave rise to a over twisted or tight contact manifold. And then if your contact manifold is exactly symplectically fillable, then the contact invariant is non-vanishing. And this requires like some pretty heavy machinery of Hutchings and Taubes, which involves looking at a isomorphism between action filtered embedded contact homology and energy filtered Seiberg-Witten Floer homology with a perturbed with Taubes' usual symplectic contact form perturbation. And then it's expected that if your contact manifold is strongly symplectically fillable, then the contact invariant is non-vanishing. But that's some work that hasn't been completed yet. And then I just wanted to underscore that ECH has only been computed in kind of like a finite set of examples. And so we don't really have much in the way of like meaningful computations. And in a lot of these, you could just say that the differential vanished or it agreed with some Morse differential. That was kind of like one hurdle that we had to overcome. Okay, so as I alluded to in the beginning, the order of algebraic torsion is going to come from where the empty set vanishes on a page of a spectral sequence. And the filtration comes from the topological complexity of J homomorphic curves, which have ECH and Fredholm index 1 with no positive ends, because we wanted to kind of kill the empty set. And then I just wanted to underscore again that nobody is bold enough to claim that algebraic torsion in ECH is actually an invariant of the contact structure. So I didn't want to use the like usual slogan that the order of algebraic torsion is a refinement of the contact invariant, but that was kind of the intuitive like description because it's seeing something about the topological complexity of whatever holomorphic curve it is that kills the empty set. And if it's a plane, then the order of algebraic torsion is going to be 0. Otherwise, it's going to be higher. And there is a weak neutrality property. And that's where this like simple algebraic torsion comes in, but we have to restrict to a simple subcomplex of ECH and then actually establishing what the simple generators of ECH are. Like requires quite a bit of understanding of holomorphic curves so that you actually have a chain map and a weak neutrality property. I don't know if I'll get to that or not. And then, well, this is just some like index stuff for specialists, which is maybe just me and possibly Luya in this room. So I guess Helmut likes index stuff too. And I guess Karen likes indices. So anyways, there are some exciting indices lurking in the background. I've got the ECH index and the Fredholm index. You can kind of like compare and contrast. You can see in the ECH index, no Euler characteristic term shows up. And this like other index, which Michael called J, not for whatever reason, does end up being able to see the Euler characteristic because it encodes a junction in a much more slick fashion. And he discovered this like relative of the ECH index and trying to show that there was an absolute grading given by homotopy classes of plane fields in ECH. There were some differences between like this Conley-Zander index term that you define for J naught or for I. There's also a difference for the Fredholm index and partition conditions show up, but we're not going to go into that. And then you get J plus, which is how you get the spectral sequence on that you use to define the order of algebraic torsion. It just encodes some like extra information associated to the types of ends that you have of your relative homology class or J homomorphic curve. Then you have what's kind of like what starts to get you off the ground is the fact that if you have a somewhere injective connected J holomorphic curve, then its J plus is always greater than or equal to 0. And J plus is greater than or equal to a quantity that encodes something about the Euler characteristic of the curve. So there's the G, and then this stuff is like a more refined understanding of the topological information associated to the ends. But you're always gonna count kind of like each end once at least. And then we don't have to read this TLDR, but at the end of the day, you get a spectral sequence, and the DL term in the splitting of the differential is coming from the J holomorphic curves, which contribute to the ECH differential that have J plus equal to 2L. And why J plus is always even involves some things that we don't quite have the time to get into, but it's if you like are really on the ball with all the index theory that goes into defining ECH, it kind of like falls out of it. And then because the ECH differential squares to 0, that's how you end up getting this J plus spectral sequence. So the spectral sequence, you take the first page is the homology with respect to E0, E2 is the homology of D1 acting on E1, and so on. And then the order of algebraic torsion is going to be the smallest non-negative K, so that the empty set becomes 0 on the EK plus 1 page. So if the empty set is killed by a plane, then it becomes 0 on the first page, and so the order of algebraic torsion is 0. If the empty set is killed by a macaroni noodle, so it has 2 positive ends, then it's going to be killed on the second page, so the order of algebraic torsion is 1. And then the hope is that you could have some more interesting values of algebraic torsion, which is what we're planning to do when we look at more exciting tree-like plumbing graphs. And then I have like a disclaimer about.
What did you say about algebraic torsion? So it's not clear if it's an invariant of the contact form or what?
Yeah, it's not clear if it's an invariant of the contact form.
And why is because nobody did it? Or?
Because you can't prove invariance of ECH.
That's the problem.
That's the problem.
Because, going over the equivalence with Sarah-Witten Floer theory, that doesn't.
Nobody knows what the order of algebraic torsion should be on the other side. So if someone knew what the order of algebraic torsion should be in monopole Seiberg-Witten Floer homology, then he would be more certain that it's actually an invariant.
Oh, okay. Yeah, okay. Sure.
But the one kind of thing that one thing that's kind of like I don't know if I want to say like secret.
But that would mean you just get that statement for very precise contact form.
Right, for very precise.
So you construct an example, you have an explicit contact form, and then you try to do something like this. But could be if I homotop the contact form, it just collapses.
Yeah, that's the thought. It could just collapse. And then the way that we got bounds for arbitrary contact forms is to pass to this like simple algebraic torsion where you do have a weak neutrality property.
Okay.
And this like simple algebraic torsion is generated by a simple subcomplex of the embedded contact homology complex, where you basically say like, I don't want to have any like awful holomorphic curves running around in a cobordism. So you set it up so that like all the curves that could appear are forced to be somewhere injective. So you can't run into problems with the chain map.
Okay.
But you still don't have like that simple subcomplex of ECH is still not invariant, but you do get a bound on what like non-simple algebraic torsion can be. And then in some situations, like the one that we're in, we have like a reasonable cobordism that we can write down and still have like a bound appear on algebraic torsion. And the kind of like weak neutrality property that I was alluding to is that this like AT simp of whatever's on top of your exact symplectic cobordism is an upper bound for whatever like algebraic torsion is for the bottom end of your exact symplectic cobordism.
Can you repeat that, Joe, please? Sorry. So what's this AT simp? I missed.
Oh, AT simp So it's, you compute algebraic torsion for the simple subcomplex of embedded contact homology. And the simple subcomplex of embedded contact homology is not, well, I said it was not simple to define.
Absolutely.
But it basically has to do with like, you only want to have some generators of ECH so that you can rule out multiply covered curves appearing in a cobordism. Where you have the stuff associating to the simple subcomplex at the top of your cobordism. Yes, with my last minute remaining, I'll just maybe end here, and then if people have questions, I can like tell you all the ingredients that we use to compute algebraic torsion, and a lot of it just boiled down to
What is that sentence? How hard can it
be to compute algebraic torsion? So how hard?
AT of okay.
Sorry.
I'm with you.
Okay. Yeah, and so basically like we had the time of our life. Well, it was actually kind of fun to like construct by hand a holomorphic plane and then realize that there was like a more sophisticated way than just writing down an ODE and completing it. But there was like a way to do it in a toric setting using a Morse flow line and a singular fiber. But then once you have this plane, you either want to show that it's unique or that it's not unique. And that kind of corresponds to the vanishing or non-vanishing of the contact invariant. And then that's also like what we ended up using to see if AT simp was infinity, or if the algebraic torsion vanished, or if we couldn't really say anything other than like AT simp was positive. In this case, like the toric methods know more because if the angle between the two rays is pi, then you have a tight contact structure, but our like all of our holomorphic curve toolkit couldn't tell us anything other than like this AT simp is greater than 0. So I'll stop here.
And what's the last line there?
Oh, the last line are like all the steps. And then here's like the definition of like what it means to be simple. So I'll just
Okay, let's think.